Another potential end for a galaxy is its plunge into a galactic cluster. In these gigantic assemblages, which contain thousands of similar systems, there are reservoirs of hot, sparse gas, known as the intracluster medium, ICM. Despite its apparent emptiness, the ICM can compress the gas clouds of a galaxy until the gas pressure tears the galactic structure apart. What if a galaxy collides with another, larger one? In this case, their supermassive black holes will merge, unleashing streams of radiation, while the supplies of gas needed for star formation will be depleted. The process may take hundreds of millions of years, but it will ultimately lead to the cessation of new star formation. However, even if a galaxy manages to avoid all these catastrophes, it still faces a slow fading due to gravitational interactions between stars. This process will stretch over trillions of years, Sutter notes, but the end is inevitable. What awaits our Milky Way? It is quite likely that its fate will be decided in about 4.5 billion years, when it collides with the Andromeda Galaxy. But what is the likelihood that this collision will actually occur? For now, it is impossible to say for certain. Although the radial velocity of the Andromeda Galaxy relative to the Milky Way has been measured at about 120 kilometers per s, its transverse speed or proper motion remains a mystery. It is known that the galaxy is approaching us, but its exact trajectory has yet to be determined. Indirect measurements suggest that Andromeda's transverse speed does not exceed 100 kilometers per s, which implies a collision of at least the dark matter halos of the two galaxies, even if their disks do not collide directly. The Gaia telescope, launched by the European Space Agency in 2013, is attempting to refine this data by measuring the positions of stars in Andromeda. Computer models created based on the research of Chris Melio and Lars Hernquist predict that the galaxies will indeed merge within the next 5 billion years. However, before that, in about 4 billion years, the Milky Way may absorb the Large and Small Magellanic Clouds. Such events are not uncommon. Andromeda has already experienced a collision with a dwarf galaxy in the past, and our galaxy has a similar history. But even more astonishingly, galactic winds, powerful streams of gas and plasma expelled from galaxies, may play a crucial role in altering their structure and evolution. What processes trigger these winds, and how do they change galaxies throughout their existence? Galactic wind is a high-speed flow of charged particles resulting from powerful phenomena in galaxies. The primary sources of such winds are young, massive stars, density waves, and supermassive black holes. Galactic winds are most commonly observed in galaxies with active star formation. This phenomenon involves the ejection of a significant amount of material, including both hot and cold gas, which, through interaction, transforms kinetic energy into thermal energy. As a result of these processes, superheated gas is formed, spreading over considerable distances, sometimes comparable to the size of the galaxy itself. In galaxies with active nuclei, the winds can also be regulated by supermassive black holes. Using the James Webb Space Telescope, scientists discovered the oldest wind on a galactic scale, erupting from the bright quasar J1007 plus 2115. This wind ejects gas and dust from its host galaxy, leading to a cessation of star formation, effectively rendering the galaxy dead. The light from the quasar traveled to us for 13.1 billion years, allowing researchers to see how it looked just 700 million years after the formation of the universe. This is the third oldest known quasar, but it is the first time such an ancient wind has been recorded, ejecting up to 300 solar masses annually at a speed of 7.6 million kilometers per hour. This process led to the halting of black hole growth and the cessation of star formation in the galaxy. Galactic winds are believed to play a crucial role in the evolution of galaxies by facilitating the expulsion of gas and the spread of metals, and at times even ejecting material beyond the galaxy into the intergalactic medium. One of the most notable examples is the Cigar Galaxy, M82, where researchers, using the Sophia Observatory, a joint project between NASA and the German Aerospace Center for the Development and Use of a Cassegrain System telescope, found that the galactic wind carries away a vast amount of gas and dust, equivalent to between 50 to 60 million solar masses. These winds also influence the magnetic field of the galaxy, stretching it over 2,000 light-years, which has been confirmed by recent observations. The results of the study of the M82 galaxy were published in the astrophysical journal Letters in January 2019. Modern tools enable astronomers to study the magnetic fields of galaxies in detail by observing infrared radiation. For instance, the Hawk Plus camera, an infrared camera and polarimeter designed to obtain images of total and polarized flux in the far infrared range, covers 5 broad bands with wavelengths ranging from 50 to 240 micrometers. The diffraction-limited visualization provides spatial resolution of approximately 5 to 20 arcseconds, with field of views ranging from 2 to 10 arcminutes. The Hawk Plus camera is equipped with 3 matrices of 31 x 40 pixels. 2 are used to record the reflective component, and 1 to register the transmitted component of linear polarization. To achieve an operating temperature of about 0.10.2 K, the detectors were cooled using an adiabatic demagnetization refrigerator. The process of bringing HARCI Plus into operation began in late 2016, and its acceptance tests were completed in late 2017. Since 2018, the instrument has been available for use as part of Cycle 7 observations. Recent discoveries regarding the quasar J1007 plus 2115 and its wind add new insights into the impact of supermassive black holes on the evolution of galaxies. These processes may have been widespread in the early universe and played a significant role in the formation of the first galaxies. However, even the most powerful galactic winds cannot explain everything we observe in galaxy dynamics. Pulsars and magnetars, unusual cosmic objects possessing the strongest magnetic fields in the universe, may play a role in understanding the processes occurring in these galactic systems. What mysteries lie hidden within these enigmatic objects? Pulsars and magnetars are among the most exotic and powerful objects in the universe, representing types of neutron stars that form after the explosion of massive stars in supernovae. These dense stellar remnants possess colossal mass packed into a sphere about 20 kilometers in diameter, making them some of the densest objects known to humanity. Despite their small size, pulsars and magnetars have a profound impact on their surrounding space, particularly due to their magnetic fields. A pulsar is a cosmic object that emits radio waves, radio pulsar, visible light, optical pulsar, X-rays, X-ray pulsar, and gamma rays, gamma pulsar. These emissions reach Earth in the form of periodic bursts or pulses. According to the most widely accepted astrophysical theory, pulsars are rapidly rotating neutron stars with a strong magnetic field tilted with respect to their rotation axis. This inclination causes regular pulses to be detected on Earth. The first pulsar was discovered in 1967 by Jocelyn Bell, a graduate student under Anthony Hewish, using the radio telescope at the Mullard Radio Astronomy Observatory of Cambridge University. This pulsar was later named PSRB 1919+21. In the initial months following the discovery, the observation results were kept secret, and the pulsar was designated as LGM-1, Little Green Men, reflecting early speculations about the potential artificial origin of the signals. It later became clear that these signals originated from neutron stars, leading the astrophysical community to conclude that pulsars are nothing more than neutron stars emitting collimated beams of radio radiation. In 1971, with the help of the Uhuru Observatory, X-ray pulsars were discovered, sources of periodic X-ray emissions that, like radio pulsars, are neutron stars with powerful magnetic fields. However, their emissions occur due to the accretion of matter from a companion star, distinguishing them from radio pulsars, which expend rotational energy to emit radiation. Radio pulsars gradually slow down over time, whereas X-ray pulsars can accelerate due to incoming material. Scientists continue to study pulsars, and their findings are intriguing. For instance, in 2015, the first gamma pulsar outside the Milky Way was discovered, and in 2016, the first X-ray pulsar was found in the Andromeda galaxy. Beyond pure scientific interest, signals from pulsars can be utilized for spacecraft navigation and as time standards. Pulsars are also the subject of research regarding the possibility of habitable planets. Astronomers from Leiden University proposed that super-Earth-type planets located at a certain distance from a pulsar could possess a sufficiently dense atmosphere to shield against intense radiation and retain liquid water on their surfaces. An example of such a system is the pulsar PSR-B 1257+12, which has 3 planets, 2 of which are at suitable distances to potentially support life. Magnetars, in turn, are characterized by even more powerful magnetic fields that are billions of times stronger than Earth's. A magnetar is a specific type of neutron star with an exceptionally strong magnetic field that can reach values of up to 10 circumflex 11 Tesla. Theoretical predictions for the existence of magnetars were made in 1992, with the first observational confirmation occurring in 1998, when a powerful burst of gamma and X-ray radiation was detected from the source SGR 1900+14 in the constellation Aquila. However, an event on March 5, 1979, is also associated with a magnetar. The lifespan of these stars is about 1 million years, and they possess some of the most powerful magnetic fields in the universe. Magnetars are a relatively unexplored type of neutron star since most of them are located at considerable distances from Earth. Their diameter is approximately 20–30 kilometers, yet the mass of most magnetars exceeds that of the Sun. For example, a pea-sized amount of magnetar material would weigh over 100 million tons. Most known magnetars rotate very rapidly, completing several rotations around their axes per second. They are observed in gamma and X-ray wavelengths while not emitting radio radiation. The life cycle of a magnetar is quite short, with their strong magnetic fields dissipating after about 10,000 years, after which their activity and X-ray emissions cease. It is estimated that up to 30 million magnetars may have formed in our galaxy over its entire history, originating from massive stars with initial masses around 40 solar masses. As of August 2021, 30 magnetars are known, 24 of which are widely recognized by astronomers, while another 6 are in candidate status, awaiting confirmation. An example of a well-known magnetar is SGR 1806–20. It is located approximately 50,000 light-years from Earth in the constellation Sagittarius. An explosion on the surface of this magnetar on December 27, 2004, released more energy than the Sun produces over 100,000 years and is considered the largest explosion in the galaxy since the supernova SN 1604, observed by Johannes Kepler in 1604. Magnetars are considered some of the most dangerous cosmic objects. Their magnetic fields can tear a person apart from a distance of just a few thousand kilometers. Additionally, they emit gamma rays, which can be lethal at high concentrations. Although their thin crust prevents constant outbursts, any micro crack in it can become a source of deadly radiation. In just 0.1 seconds, they can release an amount of energy comparable to what the Sun generates over 100,000 years. Despite these dangers, magnetars do not pose a direct threat to Earth for several reasons. They are located at significant distances from our planet, the closest being about 8,000 light-years away, and there are relatively few such objects in the universe. Nevertheless, tremors from magnetars can disrupt spacecraft, prompting scientists to closely monitor them in an effort to predict the behavior of these strongest magnets in the universe. These unique objects play an important role not only in the study of stellar evolution, but also in cosmic navigation. Pulsars and magnetars allow scientists to investigate extreme physical conditions that cannot be recreated on Earth. These objects serve as laboratories for studying phenomena such as quantum effects in strong magnetic fields, the behavior of matter at ultra-high densities, and the interaction between gravity and quantum physics. The study of these objects not only opens new horizons in astronomy, but also sheds light on broader cosmic processes. And what do we know about space-time turbulence? Could there be regions where the laws of physics work differently? The universe is not merely an infinite ocean of stars and galaxies. It is a true turbulent ocean of energies. In this ocean, much like ocean currents, plasma turbulence churns, transporting energy through time and space. It acts like a cosmic conductor, orchestrating the intricate symphony of particle and field interactions. For decades, scientists have sought to decipher the score of the symphony known as magnetohydrodynamic (MHD) turbulence. This theory, akin to a musical staff, describes the behavior of plasma on cosmic scales. One of the primary predictions of this theory is the transition from weak to strong MHD turbulence, occurring as energy redistributes from large to small scales. This transition, similar to a change in musical key, promises to radically alter the nature of turbulence. However, until recently, it remained merely a theoretical conjecture. Recently, researchers found evidence for this transition in Earth's magnetosphere, a kind of cosmic laboratory where various plasma processes can be observed. Using data from 4 cluster spacecraft, they discovered that on large scales, plasma exhibits weak turbulence, but as it moves to smaller scales, non-linear interactions begin to play an increasingly significant role, transforming the turbulence into strong. The study of the transition from weak to strong turbulence is not just a scientific abstraction, but a crucial step toward understanding a variety of cosmic phenomena. For instance, turbulence plays a key role in the compression of interstellar gas and the formation of new stars, acting as an accelerator of cosmic rays. Magnetic reconnection, the process in which magnetic fields abruptly change their configuration, releasing vast amounts of energy, also relies on turbulence. What makes Earth's magnetosphere an ideal laboratory for exploring the mysterious nature of turbulence? Earth's magnetosphere is the region of space around our planet dominated by its magnetic field, interacting with the solar wind, a stream of charged particles from the sun. This interaction leads to the emergence of turbulence, which can be studied using spacecraft. But can we find similar laboratories elsewhere in the universe? Such conditions may exist in the magnetospheres of other planets, in the vicinity of black holes and neutron stars, as well as in star-forming regions. Cosmic turbulence is a complex and multifaceted phenomenon about which we still know too little. What processes cause stars to move in flows, and what can this tell us about the past and future of galaxies? The stellar stream is a collection of stars orbiting around the center of a galaxy, which was once a globular cluster or a dwarf galaxy, but is now dispersing and elongated along its orbit due to tidal forces. How do they form? Understanding the cause and evolution of stellar stream formation was aided by the observation of the globular star cluster Palomar 5 during its destruction. The star cluster has stretched over a length of 30,000 light-years, forming a stellar stream. Astronomers state that there is a massive population of black holes within the cluster, with around 100 of them located at the cluster's center. The number of black holes is approximately 3 times higher than expected based on the number of stars in the cluster, indicating that more than 20% of the cluster's total mass consists of black holes, according to study author Mark Gills. The research models the orbits and evolution of each star in Palomar 5, from the formation of the cluster to its eventual dissolution. Researchers adjusted the initial properties of the cluster until a good match was found with the observational data for the stream and the cluster. The team discovered that Palomar 5 formed with a lower proportion of black holes, but stars left the cluster over time more efficiently than the black holes did. As a result, the proportion of black holes gradually increased as the number of stars decreased. Black holes dynamically inflated the cluster through gravitational interactions, leading to an even greater number of stars escaping the clusters and forming an entire stellar stream. The study shows that the presence of a large population of black holes might have been common in all clusters that formed streams. This could also apply to dwarf galaxies that also formed stellar streams. Research on stellar streams provides insight into how our galaxy merged with other smaller galaxies, shaping its current structure. How might the quantum foam of the universe influence the further development of galaxies? Quantum foam, also known as space-time foam, is a concept in quantum mechanics first proposed by John Wheeler in 1955. It is considered a fundamental basis for the structure of the universe. What are the mysteries and enigmas concealed behind the experimental evidence of the universe's quantum foam? The MAGIC telescopes made an intriguing discovery related to the gamma radiation emitted by the blazar Markarian 501, MARC 501, a galaxy with an active core whose spectrum extends to gamma rays of extremely high energy with a jet directed towards Earth. Researchers found that the gamma-ray photons arriving from this object did so at different times. While analyzing the data, the team sorted high-energy and low-energy gamma quanta, recording each flare. The results showed that high-energy and low-energy photons appeared to be emitted simultaneously, but the high-energy photons arrived 4 minutes later after traveling a distance of approximately 500 million light-years. This phenomenon may suggest that high-energy photons traveled more slowly, creating a contradiction with the principle of the constancy of the speed of light established in Einstein's theory of relativity. One possible explanation for this observation is the inhomogeneity of quantum foam, which could affect the speed of light propagation. However, later experiments failed to confirm this hypothesis regarding the change in light speed associated with the graininess of space. Additionally, other studies that utilized the polarization of light from distant gamma-ray bursts also yielded contradictory results. Research in this area continues and will persist into the future. What other mysteries does the cosmos hold? And what do we know about the enigmatic process of black hole collapse? Gravitational collapse refers to the rapid compression of objects under the influence of gravitational forces and is one of the key mechanisms in the formation of objects in the universe. This process leads to the fragmentation of gas clouds into distinct clumps, which, in the case of star formation, are referred to as globules. Due to the uniform distribution of matter, clusters of galaxies, galaxies themselves, and individual stars are formed. In the evolution of an individual star, the collapse halts when nuclear fusion reactions commence, resulting in an increase in temperature and, consequently, gas pressure. However, the dynamics of gravitational collapse can be more complex than in an idealized scenario. The formation of a black hole is not an instantaneous event at the conclusion of overall collapse. It is characterized by the presence of a density gradient within the collapsing object, which changes from the periphery to the center. Each spherical region of the initial radius of the collapse has its own event horizon and its own time to reach it. Here, the time increases with the growing volume or radius of the region, leading to a temporal delay of more massive regions relative to those positioned lower down. The process of black hole formation and growth begins with the formation of a quantum-sized seed 0.7777 seconds after the onset of stellar collapse and concludes after 1.4166 seconds. For a maximum mass star of 450 solar masses, formation begins after 1.342 seconds and finishes in 1.096 seconds. During the formation of a black hole, various stages of collapse overlap, making their physical distinction challenging for an external observer. An important concept in this context is the visibility horizon, which is regarded as a dynamic equivalent of the event horizon. During the collapse, the visibility horizon increases. However, due to the rapidity of the collapse, the formation of a firewall does not have time to occur. As a result of absorbing relic radiation, the growth of the black hole never ceases, and a completed event horizon is never formed. To study the process of black hole growth, it is necessary to determine what additional mass must accumulate at a distance from the event horizon. For the minimum stellar mass of a black hole, the energy flux of relic radiation is significant, corresponding to the absorption of a large number of hydrogen atoms per second. These estimates increase depending on the mass of the resulting black hole, creating intriguing opportunities for further astronomical research. However, despite the progress made, many questions remain unanswered, which scientists strive to address. What other mysteries lie hidden from us? And how might they help us unravel the enigmas related to the shape and structure of the universe itself? In ancient times, people believed that the Earth was flat. However, over time, it became evident that they were mistaken. Now we may also be wrong about the shape of the universe. The general theory of relativity describes a four-dimensional space where time serves as the fourth coordinate. According to this theory, any massive body distorts this space, and the total mass of the universe transforms its flatness into a sphere. However, the exact shape of this space remained unknown, with most scientists leaning toward the idea that it resembles a torus. Cosmologist Grigor Aslanian from the University of California presents a different perspective. He argues that the shape of the universe depends on the extent of its coordinates. It may be finite in all three spatial dimensions, have two finite dimensions and one infinite dimension, or two infinite dimensions and one finite dimension. Aslanian does not consider three infinite dimensions. In each of these scenarios, the space would take on its unique four-dimensional shape. More importantly, Aslanian developed a method to test which of these possibilities corresponds to our universe. He compared his theoretical calculations with data obtained from the WMAP space probe, which investigates the distribution of cosmic microwave background radiation in the sky. However, a problem arose. Aslanian soon realized that a conventional computer was not capable of performing such complex calculations. As a result, he turned to a distributed computing system called GRID, which spans multiple computers over an internet-like network. These calculations were easily parallelized, and the 500,000 hours required to obtain results were reduced to a much more manageable time frame. The results confirmed his expectations. The scenario with three infinite dimensions was rejected. The scientist discovered that space has the shape of an elongated torus, akin to a bagel stretched in the direction of the recently discovered axis of evil, an area in the sky where the values of cosmic microwave background radiation differ from those in other directions. Aslanian hopes to more precisely determine the shape of the universe by obtaining data from another satellite called Planck in the future. What mysteries do solitary cosmic objects wandering through the vastness of space conceal? And what secrets might they reveal about the origin and evolution of our universe? Wandering planets, also known as rogue planets, are planetary mass cosmic objects that move through space independently of any stars. These objects remain poorly studied, largely due to the difficulties in detecting them. Recent research conducted by scientists from Queen Mary University of London has shed light on the emergence of wandering planets. The study, published on the scientific portal RxEve, established that such planets can form in protoplanetary disks around young stars or originate in gas dust clouds. Under certain conditions, planets within star systems can leave their orbits and drift into open space. In the new study, researchers conducted a series of simulations to determine what causes planets to be ejected from their orbits and embark on a free journey through interstellar space. The simulation results indicated that the primary source of wandering planets is binary or circumbinary star systems, where objects orbit around a pair of stars. Over the course of their existence, such systems can eject between 2 to 7 planets with Earth-like masses into space. However, for giant planets exceeding 100 times the mass of Earth, the ejection frequency is only 0.6. The simulations took into account parameters such as the initial mass of the disk, the influence of the external environment, and the level of turbulence within the disk. Each simulation covered a period of 10 million years, sufficient for a complete system to form. In the future, astronomers plan to investigate which types of stars most frequently eject planets into space. And how many wandering planets exist in our galaxy, the Milky Way? Estimates of the number of wandering planets in the Milky Way reach up to 50 billion. Our galaxy contains at least 300 billion stars, and some studies suggest that this number may reach up to 1 trillion. Many of these stars have planets, as has been confirmed experimentally. However, recent claims by researchers regarding the large number of rogue planets have been particularly surprising. For example, consider exoplanets. Astronomers have yet to reach a final consensus on the naming of exoplanets, which are planets orbiting other stars. Currently, more than 4,000 such objects are known, and this number continues to grow. Astronomers estimate that the number of exoplanets is comparable to the number of stars, as some stars have no planets, while others may have many. An official name for wandering planets has yet to be determined, as adding the prefix exo to them is inaccurate. They drift alone through the Milky Way. To date, about a dozen such objects have been discovered. Data obtained through statistical counts and computer simulations suggest that there may be at least 50 billion wandering planets in our galaxy. For example, the trapezium star cluster in the Orion Nebula, located 1,200 light-years away, was used as a case study. In the simulation of this region of the galaxy, 1,500 stars were used, and according to the results, about 500 stars orbit 2,522 planets. It is estimated that within the next 11 million years, 357 of these planets will leave this area, beginning their free journey. Projecting these results across the entire Milky Way yields the estimate of 50 billion wandering planets. But why do planets leave their homes? To understand why planets abandon their parent systems, it is essential to consider the conditions in which they exist. If a star cluster is dense enough, interactions between stars become intense, which can lead to disturbances in the orbits of surrounding objects. As a result of these interactions, some planets and asteroids may leave their habitats. Another reason for ejections is the interaction between planets within the star system. When two massive objects approach dangerously close, one of them may lose stability and be ejected beyond the influence of the star. Such bodies cannot form in the interstellar medium. Visually detecting a wandering planet is nearly impossible, as it moves in the vacuum of space without any external illumination. Some researchers believe that such planets can remain sufficiently hot for some time due to internal processes. However, they will eventually cool down to nearly absolute zero, making the detection of any life or geological activity unlikely. The universe continues to astonish with its surprises. Researchers, unable to directly observe such objects, are finding new approaches to study them, opening new horizons in astronomy. What are the mysteries of cosmic time loops, and can they open doors to other dimensions or alter our views of the past and future? What unique experiment did physicists conduct that shocked the scientific community, and how might this discovery influence our perception of reality? In a revolutionary experiment delving into the complexities of quantum physics, a team of researchers from Cambridge University has created a simulated time loop using quantum teleportation. This theoretical study of time manipulation opens new pathways for understanding fundamental aspects of quantum mechanics. Although the concept of time moving backward remains a hypothetical construct in the real world, the innovative experiment conducted by a team led by David Arvidsson-Shakur allows for a glimpse into the potential applications and implications of such a phenomenon. The scientists employed quantum teleportation schemes involving entangled particles and demonstrated the possibility of altering initial parameters after they have been established, effectively rewinding time in their model. Arvidsson-Shakur explained this concept using the analogy of sending a gift. Imagine you plan to send a gift on the first day so that it reaches the recipient on the third. However, you cannot learn their preferences until the second day. In the conventional flow of time, this is impossible. But in their model, thanks to manipulations with quantum entanglement, you can change the sent gift to the desired one using reverse actions. Quantum teleportation played a key role in the experiment, allowing for the instantaneous observation of changes in one entangled particle when manipulating its pair, thus enabling the transmission of information through time rather than space. To conduct the experiment, physicists entangled two particles and altered one of them, affecting the previous state of the other and changing the initial outcome. However, the researchers emphasized that the time loop does not exist in reality, but is modeled for entangled quantum particles. Calculations indicated that the time loop could be successfully utilized in only 25% of cases, which is a relatively low probability. Nevertheless, physicists consider this a promising sign, indicating the potential for testing the model in real experiments. The next step in the research involves entangling a larger number of photons and utilizing the time travel simulation to change their state after entering a specialized chamber equipped with a filter that allows only photons with updated information to pass through. Successfully detecting these photons would serve as evidence that the simulation is functioning. Arvidsson-Shakur noted the difference between their development and a practical time machine. Our development is not a time machine, but rather a deep dive into the foundations of quantum mechanics. These simulations will not allow you to go back and change the past, but they will help create a better tomorrow by addressing yesterday's problems today. In a world where time flows uniformly for everyone, regardless of location. This experiment serves as a reminder of the dynamic nature of our universe and the profound impact of quantum mechanics on our understanding of time. This discovery contributes to the study of the complexity of time and its flexibility under various conditions, from black holes to dark energy. Are there parallel universes? And what scientific theories and experiments might confirm or refute their existence? The concept of multiple worlds, proposed by Hugh Everett in 1957, aims to explain random events occurring at the quantum level of matter. According to this theory, parallel universes arise to account for the decay of radioactive atoms, which occurs spontaneously and randomly. Each atom has a probability of decaying within a certain time frame, but it is impossible to predict exactly when this decay will happen. This raises the question: how does the universe decide when this will occur? According to the multiple worlds concept, the universe does not make decisions. Instead, both events happen. This means that the universe splits into two parts. In one, the atom decays, while in the other, it remains intact. Thus, these universes infinitely multiply, creating numerous variations, but there is no interaction between them. This implies that none of these universes can communicate their existence to the others. The primary competitor to the multiple worlds theory is the Copenhagen interpretation of quantum mechanics. In the classic thought experiment of Schrödinger's cat, the cat is simultaneously alive and dead until someone opens the box and forces the cat to assume one of two possible states. In the context of the multiple worlds concept, no choice is made. There are simply two universes. However, for any individual observer in either universe, both interpretations appear the same. Although experiments have been proposed that could help determine which of these theories is more accurate, their implementation requires quantum computers, which have not yet been invented. How far can we look into space? The boundaries of the observable universe represent one of the most fascinating topics in modern astrophysics, as they raise questions about how far we can look into space and what lies beyond our current observational horizon. Scientific theories suggest the existence of a much more extensive cosmos, possibly even infinite. What we observe is merely a small part of the entire reality. These observational limits not only spark curiosity, but also pose numerous other complex questions for scientists. What are the physical laws beyond our horizon? Are there other galaxies, stars, or even life that we cannot yet detect? Observing the distant regions of the universe provides a unique opportunity to study its evolution and structure. How many more mysteries and wonders lie beyond what we can see? And how might they change our understanding of the cosmos itself? Subscribe to the channel and stay tuned for the latest discoveries and research in space.